Welcome everyone in the lecture 1 of pavement design tutorial. The subject will mainly talk about parameters such as what are the regional factor which plays important role in the pavement design, what are the Excel loading criteria, how the thickness response and thickness depth is usually assigned to the structure, what is material stiffness, and how we determine the structural number and frost depth and so on. But these all are a very broad term. If you will stay with me till the end of a lecture, that will be a kind of a series of the lecture. So I hope that at the end of a lecture, after within 6 to 7 lecture, each and everyone will learn and understand that how we can design the pavement under different method. In this lecture, we will mainly talk about what is flexible pavement stress analysis. We will also talk about the numerical models. We will also talk about what are the available model through which we can design the flexible pavement. We will also talk about falling weight deflectometer. We will also talk about multi-elastic theory. We will also talk about one layer system, Boussinesq system, and we will also talk about Foster and Ahlvin method as well. Coming to the very first slide, when we talk about the pavement analysis or how we design the pavement, so we usually deal with importantly with so many parameters, but the main which really play their role in the pavement life or in the deterioration, which actually bring the life to zero, or like the life of a pavement to fail, or the two important parameter, one is stresses and another one is strain. Is each and everyone have little bit idea about both of them. So the stresses are basically the load acting per area. Whenever we have the circular load, the uniformly loaded circular area, when the load is acting on the circular area, so because of the stresses, when it reach to its yielding limit or elastic limit, when the same phase of a stresses convert from stresses to the strain, then we almost reach to the level which is almost we call the deterioration level or the failure level. So when we with the passage of time, when the same effect reach to the and appear in terms of a cracking and rotting, that's the analysis which we will learn today in this whole session. We have many models through which we can compare and compute and determine the deflection, stresses and strain, such as, but all of them have different capabilities. Capabilities means like the one is quite unique to determine the deflection, but have some issues with strain because of the limitation, because of the confined strategy. The second important thing which is which plays a very important role in analysis is the assumption which we consider below the surface. So the underlying assumption are very much important parameter, which is again quite different strategies, such as one layer system, two layer and multi-elastic layer theory, and then the rigid pavement model, and then Ahlvin model. All of them, they have different underlying assumption which really affect on the stresses and strain and deflection values. Few of the numerical models are quite complex to understand and apply because of the sophisticated data which is needed from the field. Sometimes theoretical to determine the theoretical data is possible, but in reality it sometimes is not possible to determine the same type of a data which is according to the requirement of the model from the field. And then we have of course the material deformation or like material requirement information, such as where we usually determine the material stiffness or material response to the heavy loads. So This is a very big kind of a major assumption, or like kind of a negative aspects which is already available in so many models. But if we talk about the ideal model through which we can determine the stresses and strain, so we usually provide the two types of a input parameter. Number one is a static loading and another one is dynamic loading. The second important parameter through which we can also, which is kind of a needed for all those models to determine the stress, strain and deflection, is also the material properties, traffic counts, traffic information, as well as the environmental and demographic level as well. But all those model, all those information, if we put all of them together, so now the question is which model to use, which model not to use, and what are the drawbacks of all those models which are exist. So the question is there any defined model through which we can now analyze all those stresses, strain and deflection, which is kind of acceptable, and according the result is also validated. So the available model we have, the first one is multi-elastic layer theory. So the available model we have, the first one is multi-elastic layer theory, the second one is FEM model, the third one is viscoelastic theory, the fourth one is dynamic analysis, while the fifth one is thermal model. All those models are widely used, but in the specific scenario, such as thermal models are used when we have the temperature variation and changes, dynamic whenever we have the changes in inertia, while the viscoelastic is only dependent on the time and temperature, while the FEM is kind of finite, so you cannot make it like more viable, while the multi-elastic layer is also used, but it's completely based on like two things. We also need the lab testing as well as the field testing as well. So usually we use multi-elastic layer theory, which is kind of a complete model, but we can also use the remaining four models as well. Maybe some of you heard this word before. This is a falling weight deflectometer. The purpose of this falling weight deflectometer is to evaluate or compute the physical properties of a pavement, such as the structural capacity, the overlay design, and also to determine if pavement is overloaded. So the question is how basically it works. We have one small trailer through which we usually drop the weight from the top, and then the geophones and sensor are basically installed in the pavement lower surface, through which we determine the deflection model. As you can see here, it gave us a model, and from that model we usually determine the responses of a deflection. But through falling weight deflectometer we usually determine with other parameter, mainly the like deflection. So welcome in the multi-elastic layer theory. What is multi-elastic layer theory? It's very much important that you should understand the basic parameters regarding those theory, because the same thing will actually continue on with passage of time. So to determine the vertical stresses due to a uniform distributed load, according to the multi-elastic layer theory, which is quietly used nowadays in the design parameter, we assume that each layer is continuous, and it have also the homogeneous property. Homogeneous means, as you can see here, we have the three layer system. So the very top one, you can assume the one where we have a Z1 is a base course, while the Z1 is a sub base, while the Z3 is a subgrade. From the top we have a uniform distributed load, which we call UDL, okay. But if we consider the same dynamic loading, so then we will call it UCLA, uniform uniform distributed circular area loading. Okay, A is basically a radius, while Q is a pressure, and Z determine the depth, while E is a elastic modulus, and so on. Okay. If you talk about the freedom which we usually get from the multi-elastic layer theory, as you can see here, whenever we have a loading in a UCLA form, so we can determine the stresses, strain, and deflection below that specific loading parameter, such as mentioned at point A and point B. So we can determine basically through multi-elastic layer theory, we have a freedom to determine the stresses at any point below line. Okay. Now we will talk about the one layer system, which is basically determined in 1885. According to that system, the point load on an elastic space were actually assumed that the entire material below that specific loading is homogeneous and isotropic, as well as the elastic in nature as well. But the only point here, which was, you can call the negative aspect as well of the Boussinesq equation, which were determined in 1885, he considered the load is a point load. But through that system, we can also determine the vertical stresses, as well as or represent the radial distance from the load. Basically, the point where we have the sigma z, which we call vertical stresses, where we basically want to determine. So that means that you can change that point anywhere. So if your point is if your load is acting at any specific point, so you can move that point anywhere. Okay. And Z is basically the depth, which is determined in terms of a thickness, while the P is the loading. At the right side, we have the sigma Z formula as well, through which if we have all the parameters such as radial distance, depth, and point loading, so then we can determine vertical stresses at any point. Okay. According to the one layer system, the point load, because of the point load, because the pavement, the next chart is also because of the modification in 1885. Then Foster and Ahlvin, they basically improved the same model, and they mentioned that not only vertical stresses, but we can also determine the radial stresses, tangential stresses, shear stresses, as well as deflection. They basically improve the system and develop a kind of a chart, and they also mention that this is a kind of extended version of a one layer system, and they also mention that this is not the limitation of the one layer system to only determine through that theory the vertical stresses, but they also come up with a model, so that they mention that we can also determine the radial and tangential stresses as well in different direction, under the different depth, as well as in the different offset as well. This is basically the chart which usually follow through that method. As you can see here on the top, we have a formula as well. Okay, so which is basically P divided by Q multiplied by 100, which is through that we can determine the stresses as well. So the right side, we have the R by A. What is R? R is basically radial horizontal distance, while A is basically a radius of a circle. So from the R by A, and on another side we have a Z by A. Z is basically the depth or the thickness depth divided by the radius. So we can determine the shear stresses because of the circular loading, in Foster and Ahlvin method, which is basically the modification of the Boussinesq equation in 1885. This model was improved in 1954. This is one typical example which is already resolved for you people as well. As you can see here, we have the load is acting from the top. Okay, the circular loading is coming, which is 9,000 labs pound, and the pressure is around 80 psi. So the depth is exactly 6 inches, while we want to determine the R at 6 inch as well. Okay, as you can see here, the value of a Z and R, you can move it according to your understanding, according to your definition. What is our purpose? To determine the sigma Z. Okay, according to the Foster and Ahlvin method, we can determine the stresses at any level. Okay, which is basically equal to the kind of a factor. Okay, so Boussinesq stress factor divided by P divided by Z. Okay. Here you can see here that how we determine. So we have the value of R, we have the value of Z. Okay, we want to put all those two values to determine the R by A and Z by A, which is I already mentioned in the previous chart. So we can determine the vertical stress distribution. So from that formula, which is quite simple, in terms that Q is equal to P by A, right? So but the A is equal to pi R square, where R in that one layer system we already assign it to the radial horizontal distance. So we denote R with A. So if we want to determine A, which is equal to A is equal to pi R square. So after the changes in the same formula, we got A is equal to P divided by Q pi into which is closed in the bracket. Okay, so as you can see here on the very top, we have formula. Okay, we can determine like the formula is sigma stresses at Z in the Z direction divided by Q, which is already given, which is 80 psi. We need to multiply it with 100, and from that we can determine it. So we have R by A and Z by A, which is already, so like you, first of all what you need to do is you need to select the value at the left end in the Z by A. So what is Z? If we go to exactly at the top where we have 1, and then you need to come to the another side, which is our right side, where we have the R by A value. So from here you need to select the value exactly for 1, and the place where both value of R by A and Z by A are intersect with each other, this is basically your value. Okay, so here is almost 33 or 34. Okay, so from that Foster and Ahlvin method, when we determine here or value, so we will put that value in our model, which is sigma Z is equal to the value 33, which is already determined from our graph, while 80 is a psi. 80 is basically the pressure which was already given in psi, and divided by 100 we have 26.4 psi. So that means that at a depth Z and a radial distance A, horizontal radial distance A, we have the vertical stresses level is almost 27 psi. From the same formula, we can also determine the value of deflection as well. As you can see here, is if we have a flexible pavement, or if we have a rigid pavement. Okay, so we can put there different formula. So from the same formula, we can also determine and you can also compare it, that which one rigid will be higher. either flexible or either the one in the rigid. But because of the parameter, we cannot determine it. But in the future, I mean, okay.